Hey guys, welcome back to the video. We're going to be covering the combinatorial circuits, which is the main part of the level 2 standard. So in combinatorial circuits, there are components connected in series and there are components connected in parallel in one circuit. Okay, so basically, I've written that a combinatorial circuit consists of certain components connected in series while some are connected in parallel. In these cases, components connected in series and in parallel should be considered separate. Okay, so for example, this component in series is separate from the components in parallel. Okay, so when doing the calculations, you should isolate them. So total resistance of series plus total resistance of parallel. Okay, so you isolate them and you don't use them together. Alright, the characteristics of a combinatorial circuit. So basically, the voltage is shared between the components in series and the voltage and the components in parallel. The components in series will use a certain amount of voltage. The remaining voltage is equally distributed to the components in parallel. So what I'm basically trying to say is, for example, once again, coming back to our example of the candy. So the students, they're going to pass through a classroom. So this classroom, there's only one route you can go. So the students have to go through this classroom. So when the students go through this classroom, they're going to drop off some of their candy. So therefore, when they get to the parallel circuit, they'll have less candy remaining. And when they have less candy remaining, some students will go this way, and some students will go path 1, some students will go path 2. However, the students have the same amount of candy left. So path 1 and path 2 gets the same amount of candy. So therefore, the remaining candy gets evenly distributed throughout the parallel circuits. If a component is connected in series, the total resistance decreases, but if a component in parallel is removed, RT increases. Okay, basically, coming back to what I was saying. So, component in series, there's a body guard standing in front of it. If I remove that, then the total resistance decreases because in the series circuit, R total equals to R1 plus of R2 plus of R3. But if the parallel RT is removed, that's basically saying that there's one less checkout. So therefore, once again, the RT would increase. So basically, just combining both the logics together. And lastly, if there are multiple components connected in one pathway of a parallel circuit, the voltage through the parallel circuit is shared between the components. So what I'm trying to say is, for example, the students come to the fork. So some students will go pathway 1 and some students will go pathway 2. For example, let's say half of the students went pathway 1, and in pathway 1 there are two classrooms in pathway 1. And when I say there's two classrooms in pathway 1, therefore the students have to give some candy to classroom 1 and then some candy to classroom 2. So therefore the voltage between those series within the parallel, those two components will have a shared voltage between them. As I'm going to look through a few examples of combinatorial circuits. Sorry, my voice is a bit clumsy today. Sorry. Sandra is investigating electrical circuits in the lab. She connects various resistors in combination. The current drawn from the supply is 6 amps. Calculate the effective resistance of the circuit. Okay, so you should notice that there is a 3 ohm resistor connected in series, and there is a 4.6 ohm resistor and a 2.2 ohm resistor connected in series within a parallel with the 3.5 ohm resistor. So basically, this 4.6 ohm resistor and the 2.2 ohm resistor, first of all, you should combine these two resistors to make one big resistor. And that one big resistor is in parallel with the 3.5 ohm resistor. And then you'll find the R total for the parallel and add it to the 3 ohm resistors, okay? So basically what I've said here, the 4.6 ohm and 2.2 ohm are connected in series, which is connected parallel with the 3.5 ohm resistor. The 4.6 ohm resistor can be combined with the 2.2 ohm resistor to form one large resistor. So this is basically series, okay, just adding them up, R total equals to R1 plus R2. This large resistor is connected in parallel with the 3.5 ohm resistor. So we say 4.6 plus 2.2 is 6.8 ohms. And 1 over RT equals to 1 over R1 plus 1 over R2. If we substitute these numbers in, so RT should come out to be 2.31 ohms. So basically, like I said, the students splitting into two different ways. So pathway 1, there would be two different classrooms, and then these two different classrooms add up to create the total resistance for pathway 1. And the total resistance of pathway 1 is what we use in our calculations. So I forgot to add the 3 ohm resistor. So the 3 ohm resistor connected in the 3 ohm resistor is connected in series, so therefore it's just simply added on. So therefore 2.31 plus 3 is 5.31 ohms. Alright, so B should be calculate the size of the voltage across the 3.5 ohm resistor. So in this case, the total voltage is equal to the voltage in the parallel. So voltage given to the parallels is the total voltage minus the voltage given to the 3 ohm resistor. So basically, the students are going to give some candy to a 3 ohm resistor, and then after they're going to split and give equal amount of candies to the resistors in the parallel. So therefore, first we need to find the total voltage. Okay, so total voltage equals to total current, total resistance. Okay, so total resistance we already found is 5.31. We know that our current is 6 amps. So therefore, we multiply these two together. We found that our voltage is 31.86 volts. And now we find out the current through the 3 ohm resistor. So how much candy is given to a 3 ohm resistor, and we do the total amount of candy minus the amount of candy given to a 3 ohm resistor, and therefore we'll find the amount of current, amount of voltage given to the parallel. Okay. So 3 ohm resistor, 6 amps passes through. This is the 6 amps is gonna flow through, and it's gonna come back, and the entire 6 amps is gonna go through the 3 ohm resistor. So that's because the 3 ohm resistor is connected in series, and series means that the current is the same. So all the students are gonna pass through that 3 ohm resistor. So V equals to 3 times 6, so V equals to 18 volts. And therefore 31.86 minus 18, it will give us the 13.86 volts. And then just a final concluding statement. Because the 3.5 ohm resistor is connected in parallel, the voltage through the resistor is it's not 14.6, it's 13.86. It's a typo there, sorry about that. Alright, so now we have an explanation-based example. This is an excellence question. So Stephen connects identical labs as shown in the diagram below. Okay, just ignore part A and look at part B. Stephen replaces lamp B with a new one. Explain what will happen to the voltage across lamp B and the voltage across lamp A if another identical lamp D was added in parallel as shown in the diagram below. So by adding another pathway, so like I said, you're adding another checkout, that means the resistance decreases because 1 over R total equals to 1 over R1 plus 1 over R2 plus 1 over R3. That means that the total resistance will decrease, okay? And that means, linking it back to V equals to IR, so the total voltage of the system remains the same. That means I is proportional to 1 over R. If R decreases, then the I must increase. Alright, so each of these lamps are identical, and there are 3 pathways. So the key term here is identical, okay? This can only happen if the bulbs are identical, okay? Because the bulbs are identical, 1/3 of the current will flow to each B, and 1/3 of the current will go to C, and 1/3 of the current will go to D, okay? And that's only because the lamps are identical. If they are not identical, then this will not happen. So 1/3 of the current flows. However, when there's only B and C, let's say if we remove D, then there's only B and C. And if there's only B and C, then 1/2 of the current will go through each of these, will go through the B and the C. So therefore, the total current through each light bulb actually decreases. So therefore, the voltage V equals to IR, the resistance of the bulb remains the same, and the voltage decreases. So therefore, the current decreases. So therefore, the voltage must decrease for lamp B. However, for lamp A is connected in series. That means the entire amount of current, so the entire amount of current is going to pass through lamp A. And if the entire amount of current passes through lamp A, the current was greater than before because the R gone down. That means the I increases, and I increases. So that means I increases, and the resistance of the bulb stays the same. So therefore, the voltage at A will increase. And that's basically how you would explain for this question. It's an excellence level question. That would be how you would explain. So another practice question. Stephen then takes a selection of resistors and connects them as shown in the diagram below. Calculate the voltage across the 0.5 ohm resistor. Alright, so this is actually a pretty easy question, okay? So as you can see, the 6 amps is flowing through and it's going to go through the 0.5 ohm resistor. And that's because the 0.5 ohm resistor is connected in series. And if they are in series, then therefore the current remains the same. And all 6 volts will flow through the 0.5 ohm resistor. Alright, so this means that we can say that V equals to IR. 0.5 ohm connected in series. So we can say V equals to IR, and therefore V equals to 0.5 times of 6, which is 3 volts. And that will be your final answer, 3 volts there. So part D is calculate the resistance R. So the total resistance R. So if we calculate the total resistance of the circuit, and then we take away the 0.5 ohms from the series circuit, then we can find the total resistance of the parallel circuit, okay? So if I bring up the example of the classrooms again, so for example, there's a total resistance of this amount, and then there's one classroom connected in series, and there's one bodyguard in front of it. Therefore, if we take the total resistance and take it away from that classroom, take away that classroom 0.5 ohms, then we'll be left with the total resistance of the classrooms in parallel. Because like I said, remember what I said at the start of the video, you always treat series and parallel separately. They are not the same thing. So therefore, the 0.5 ohms is completely separate, okay? Completely separate from the parallel circuit, okay? So basically what we're saying is parallel circuit resistance plus series circuit resistance equals to total resistance, okay? Very important to keep that concept in mind. So to calculate the total resistance, we can say that V total equals to I total, R total. So therefore 12 equals to 6 times of R total, and therefore R total equals to 2 ohms. And we need to take away the 0.5 ohms from in the series. So I've written here, resistance from parallel equals to total resistance minus the resistance from the series. So therefore 2 minus 0.5 is 1.5 ohms. And now we're only left with the series circuit. Okay, we're left with one series, not series circuit. Now we're left with one parallel circuit. Okay, so now we know that the parallel circuit is 1.5 ohms, and we can use our relationship 1 over RT equals to 1 over R1 plus 1 over R2 ... And now we know what RT is. We know that the resistance total of the parallel is 1.5. So we can substitute RT equals to 1.5, and we can substitute our numbers in. So we can say 1 over 1.5 equals to 1 over R, which is our top half here, plus of 1 over 4 plus 2. As you can see, these two resistors at the bottom, they are a series within parallel. So if you're just looking at the bottom line, they are connected in series. So therefore, the total resistance of the bottom, just looking at the bottom route, the total resistance of the bottom route is 4 plus 2, which is 6 ohms. So we can add the 4 and the 2 to create a bigger 6 ohm resistor. And then the 6 ohm resistor is in parallel with the resistance R. So therefore, we can say that 1 over R plus 1 over 6 is equal to 1 over 1 over 5. Is equal to 1 divided by 1.5. And therefore 1 over R should come out to 0.5, and therefore your resistance should come out to be 2 ohms. And this is up. And this question here is an excellence level calculation question. So now I'm going to be looking at some power questions, okay? So power is measured in watts, okay? It's measured the rate of conversion of energy. So when I say power, that's basically like if I'm giving a certain amount of candy to someone, power power would be how fast this person can convert that candy into, for example, kinetic. I'm just saying this for example, okay? I'm giving a candy to someone, and power is how fast they can convert that chemical energy from the candy and convert it into some other form of energy, okay? So that's what I'm saying. So, for example, the voltage, okay? I'm giving a certain amount of voltage to a light bulb. And this light bulb is going to use the voltage and convert the electrical energy and convert that into light and heat energy. So based on how fast it can do that, okay, so how fast it can convert it is based on how, it will be how powerful it is. The most important formula to remember is P equals to IV, and this is the formula they give you in the exam. The bottom equations that are listed at the bottom, I don't think are actually given in the exam. So you'll have to remember it yourselves. So another very important point, power determines brightness. So the more powerful a light bulb is, means the more bright it is. So some other formulas for power are P equals to work over time, power equals to V squared over R, and P equals to I squared R. So most common questions involving power in the exam will require you to explain what a certain change would affect brightness of a bulb. So for example, an NCEA type of question would be like, if I removed this resistor, how would this resistor's power be affected? Okay, so that's basically what an example NCA question would be like. If I did this, how would the power be affected? So power and calculation based questions. So we're looking here. Tavita reconnects the three resistors in parallel. Tavita reconnects the three resistors as shown below. The circuit is changed so that the current through the 6 ohm resistor is now 2.0 amps. Calculate the power output of the 3.0 ohm resistor. Alright, so two things we need is power and for power, voltage and current. Alright, so we know that the current through the 6 ohm resistor is 2 amps. And that means we have both the resistance and the current. And with the resistance and the current, we can find out how much voltage. We can find out how much voltage goes through the resistor. And because the 12 ohm resistor and the 6 ohm resistor are connected in parallel, so that means when the current gets to the junction and splits, the same amount of voltage will be given to the 6 ohm resistor, and the same amount of voltage will be given to a 12 ohm resistor. So 6 ohm resistor will have a certain amount of voltage, and the 12 ohm resistor will have the same amount of voltage. So in this question, okay, we'll start off. We've already read the question, so we'll find the voltage through the 6 ohm resistor. So voltage through the 6 ohm resistor is IR. So therefore 6 times 2, okay, so resistance times times current is 6 times 2 equals to 12 volts. So therefore we can conclude that because the 6 ohm resistor receives 12 volts, and because the 12 ohm resistor is connected in parallel and the voltage in parallel are the same, 12 volts also goes through the 12 ohm resistor. So now you know that the 6 ohm resistor has 12 volts and the 12 ohm resistor also has 12 volts. One thing you also know is that when the current gets to a junction, some of it will go through the 6 ohm resistor and some of it will go down to the 12 ohm resistor. Okay, so one thing I actually forgot to explain, okay? For example, we have these two different pathways, right? We have these two different pathways, and there's a 6 ohm resistor and a 12 ohm resistor. Okay, going back to our example of the classrooms, okay? So, for example, classroom 1, there is a 100 kilogram bodyguard, but in classroom 2, there's only a 20 kilogram bodyguard. So when the students split, more students are able to get through the 20 kilogram the bodyguard. More students are able to get through the 20 kilogram bodyguard. So therefore, we can say that more students split off to the 20 kilogram bodyguard, and therefore the pathway with less resistance actually receives more current because there's less opposition there. Remember, current is very smart, okay? Current always wants to go the easy way. So when current sees there's an easier way, more of it will go towards the easier way. And then less current will go through the harder way, okay? So the 12 ohm resistor, the 12 ohm resistor is much stronger than the 6 ohm resistor, so less current is able to get through. So therefore, the current's like, I don't want to go through the 12 ohm resistor, so more of it will split towards the 6 ohm resistor, which is easier to go through. Alright, so now that we know that both of these is 12 volts, okay, we can find the current through the 12 ohm resistor and the current through the 6 ohm resistor. And if we add these two currents, we'll get the I total at the junction. So current through the 12 ohm resistor is just 12 divided by 12, okay, so that equals to 1 amp. And we know that we also know that the current through the 6 ohm resistor is 2 amps. So total current is equal to current through 6 ohm plus current through 12 ohm. So 2 plus 1 is equal to 3 amps. So now we know that 3 amps goes through the 3 ohm resistor. Okay, that's what we know now. So 3 amps goes through the 3 ohm resistor. So the next thing we've got to do is we've got to find the voltage through that resistor. So we can say the voltage through the 3 ohm resistor equals to IR. We know the voltage is, we know the current is 3. And we know the voltage, not voltage. We know the current is 3 and we know the resistance is also 3. So voltage equals to 3 times 3, which is 9 volts. And now our final step is using P equals to IV. P equals to IV, and then we can finally use P equals to 3 times 9, which is 27 volts. Okay, no, what am I saying? 3 times 9 is 27 watts, and that's your final answer. And this is an excellence level calculation question, okay? So just getting this question right will get you an excellence grade. So this is an example for power in an explanation-based question. Explain what would happen to a voltage across the 3 ohm resistor if the 12 ohm resistor is removed, but the total voltage remains the same. So that's based on the last picture. So if the 12 ohm resistor is removed, then that's completely removing one pathway. So the current can only flow through the 6 ohm resistor now. So basically that's saying that once again, back to our shopping example, one checkout has been removed and now there's only one checkout. So now there's an extra long queue, very long line of people waiting to get through that one checkout. Therefore, the resistance will increase. And if the total resistance increases and voltage remains the same, then R is proportional to 1 over I. So therefore, the current will decrease. And if the current decreases, then therefore, because the resistance through the resistance through the components are the same, so therefore the voltage will also go down. Okay, but for this question, I want to do it in terms of power. So if you're looking at this and it says what will happen to a voltage, replace the word voltage with power. Okay, just explain what happened to a power output. Okay, so first things first. Okay, if we remove the 12 ohm resistor, 6 ohm resistor is now in series, so there's only one way for current to flow. Hence, the total resistance will increase. If the total resistance increases and the voltage remains the same, I is proportional to 1 over R, hence I will decrease, the current decreases. If the current flowing through decreases and the circuit is now series, okay? And that means the 3 ohm resistor will receive a lower total current. And since it has a lower total current and the resistance of the 3 ohm resistor remains the same and V equals to IR, therefore the voltage will also be lower. And you link it back to power. Power is P equals to IV, and therefore we can say that I has gone down and the voltage has also gone down. Okay, so both of these components have gone down, so therefore the power must also decrease. Okay, so basically by removing that 12 ohm resistor, current has decreased. First of all, resistance has increased. Okay, a resistance increase will cause, assuming the voltage remains the same, total voltage remains the same, that will cause the current decrease. And if there's a current decrease, that means the current flowing through a component is less, and the current flowing through a component is less, and the resistance remains the same. Therefore, the voltage through that component will also decrease, and therefore we're coming back to our P equals to IV. Both variables have gone down, so therefore P must also go down. Okay. So trying to think of how I would explain this in easier terms. For example, if I had by increasing the resistance, the students are now harder to get through. It's now harder to get through the resistance. Therefore, the less students are able to get through and deliver the voltage to the components. And because less students are able to get through, because the resistance is increased, so it's harder for the students to get through. So only some students can get through and deliver. And these students will deliver a lower amount of voltage because there are less students, and therefore this will cause the total amount of candy in the classroom to decrease. And if there's less candy and there's less students, therefore the output of the classroom also decreases. Okay, so just just imagine it in terms of the student example, okay? By increasing the resistance, it's harder for the students to get through, okay? Just remember that. So just one final exam question practice. So question 3, doesn't matter what question 3 it is. So use the following circuit diagram to answer the questions below. Show that the total resistance of the circuit is approximately 10 ohms. So once again, we're going to be adding total series resistance to total parallel resistance. So yeah, show the total resistance is that. Resistance in parallel is 1 over RT equals to 1 over R1 plus 1 over R2, and etc. So 1 over RT equals to 1 over 4.8 and 1 over 7, okay? And your RT should come out to be 2.85 ohms. And now you can add that to the total resistance, which is incurred by the bulb in the series circuit. So your total resistance will be 2.85 plus of 7, which is 9.85 ohms, which is approximately 10 ohms. For question B, we'll need to calculate the voltage across 1 and 2. And when I say voltage across 1 and 2, we can use RT times of IT equals to VT. And when I say RT, IT, and VT, we can find out the total amount of what we're looking for, total amount of current that is flowing through. So we found our current is 9.85, but I'm going to use 10. The reason I'm using 10 is because A says that the circuit is approximately 10 ohms. So I'm just going to use 10. 12 divided by 10 is 1.2 amps. Therefore, the the current total is 1.2 amps. So now we can use V equals to IR to find the amount of voltage used on bulb 1. So resistance of bulb 1 is 7 ohms, and the current flowing through is 1.2 amps. 1.2 times of 7 equals to 8.4 volts. And therefore 8.4 volts are used on bulb 1. So therefore the remaining amount of voltage goes to a parallel circuit. So bulb 2 is in parallel with 3, so hence the voltage is the total voltage minus the voltage used in the series circuit. So the series circuit, it used 8.4 volts, so therefore 12 minus 8.4, it's not appearing, 12 minus 8.4 equals to 3.6 volts, and therefore because they're in parallel, because they were in parallel, each bulb will receive 3.6 volts. So looking at the final question, bulbs 2 and 3 are not the same brightness. Explain why. So bulb 2 has a resistance of 4.8 ohms and bulb 3 has a resistance of 7 ohms, okay, as you can see in the diagram. So they have the voltage of 3.6 volts passing through, as we saw in the last question. We can use the equation for power is P equals to V squared over R. So we can do 3.6 squared divided by the resistance of the bulb to find the power output. So for bulb 1, we can say that power equals to 3.6 squared divided by 7, which comes out to be 1.85 watts. For bulb 2, we have the same 3.6 squared divided by 4.8 this time, okay? And that equals to 2.7 watts. Now our final statement is bulb 2 is brighter because it has a higher power output. And then you have to link the higher power output to the brightness. So how higher power output and brightness are linked, and it depends on power, okay? So higher the power, the higher the brightness. So therefore, you can say bulb 2 has a higher power as it has a lower resistance, okay? So as you can see here, the denominator is lower for bulb 2, and the numerator, so the voltage is the same. So therefore, the power output for bulb 2 would be bigger than the power output for bulb 1. I hope you enjoyed the slideshow. I don't think I covered everything, but I think I covered many of the main things that students were struggling with and were asking me to explain. So I hope you enjoyed the video. If you liked the video, please drop a like down below. This took quite a bit of time, so I appreciate it if you can drop a like down below. If you have any comments below, please leave it in the comments below. And I'll see you all in the next video. Thank you. Bye.